Remember, we started this chapter by saying that there are 4 parameters for any gaseous system: pressure, volume, temperature, and number of moles. When we studied Charles' law, we defined the relationship between these two, keeping the other parameters constant. And when, I beg your pardon, this was Moore's law. Sorry about that. And then when we talked about Charles' law, we related volume of gases to temperature. And then we related number of moles of a gas to its volume using Avogadro's law. So now, in all of these cases, 2 of the parameters were fixed. When we studied the relationship between pressure and volume, we kept number of moles and temperature constant. The same, when we studied the relationship between volume and temperature, we kept amount of the gas, number of moles and pressure constant. And then when we studied combined gas law, we compared these 3 parameters together. We changed them, keeping number of moles constant. So we want to go even further, studying the ideal gas law. We want to relate all 4 parameters together. The 4 parameters of pressure, volume, temperature, and number of moles can be related together when we study ideal gas equation. So let's start. Let me clear my whiteboard. And just refreshing your mind that Moore's law dealt with relationship between volume and pressure, keeping these 2 constant. And again, Charles' law related volume and temperature, keeping these 2 constants. And Avogadro law studied relationship between volume and number of the moles of the gas, keeping these 2 parameters constant. Now, what if I combine these proportionality? If I combine these 3 experimental results together, can I say volume should be directly proportional to temperature and number of moles? And because P is on the bottom of the ratio here, volume and pressure are inversely related. That means I place pressure on the bottom. And just like what we did before, I want to convert this proportionality to an equation. What did we do before? How do you replace proportionality factor with an equation? What do I need? In other words, if I want to write V is equal to NT over P, which is the same relationship, except instead of proportionality, I'm replacing an equal sign. Did we say if you are converting proportionality to an equal sign, you need a proportionality constant? So here, I need proportionality constant. How do we obtain proportionality constant? We go to the lab, we get a gaseous system, we measure the volume, we measure the temperature, we have a given amount of a gas, we measure the pressure, we plug it in, then we can calculate proportionality constant. We have used K for constant so far. But let's use the letter R for this proportionality constant. So what is R? Proportionality constant. How do we measure it? Experimentally. So let's see how I can calculate R. If it is a constant, then I have an equation which is relating all the properties of gases together, and that would be very useful equation. So this is NT over P. This is the proportionality constant, which I was talking about. Now I need to calculate R. Once I calculate it, it's constant, it's not changing. I can use it for any problem solving related to gas laws. So let's do that. R is called gas constant. And if I want to make this equation a little bit better looking, can I multiply both sides of this equation by P? And if I do that, can I cancel P from the top, P from the bottom? Also on the left-hand side, P times V. I have PV. On the right-hand side, P on the bottom is canceled with P on the top. So I am left with N times R times T. So this is a nicer looking equation. And we call this ideal gas equation. This is called ideal gas equation. I'm going to define why we call this ideal gas equation later on. There is a reason for that name. But for now, we have developed a formula which is mother of all equations when it comes to gases. Pressure, volume, number of moles, and temperature are related together. So PV is equal to nRT. It's called ideal gas equation. But before that, let's calculate this constant. Once we calculate it, we can use it for any gaseous system. It's constant, it doesn't change. So guys, if I say, let me write the equation again. Did we say ideal gas is equal PV is equal to nRT? Now you want to calculate R. How can I solve this equation for R? Can I divide both sides by N times T? And N times T. T and T will cancel. N and N will cancel. I would be left with R only, which is equal to what? PV over NT. So if I want to calculate gas constant, I need to measure the pressure, volume, amount of the gas, and temperature. Then I just plug in the numbers in this ratio. I'll have the value of gas constant. But we already have an experimental fact. What is the experimental fact that we are talking about? Remember, we said based on experimental fact, 1 mole of any gas under the standard temperature, which is 273 K, has a pressure of 1 atmosphere. And a volume of 22.4 liters. 1 mole of any gas at the standard temperature and the standard pressure has a volume of 22.4 liters. That's what we are saying. So under the standard temperature and pressure, 1 mole of any gas has a volume of 22.4 liter experimental fact. It doesn't matter you have helium or oxygen or nitrogen. So I'm going to plot this information here. You said 1 mole of any gas, right? That's 1 mole, N is equal to 1. And the standard temperature, that means at the temperature of 273 K. That was our definition for a standard temperature. And we said the standard pressure, our definition was 1 atmosphere. We'll have a volume of 22.4 liters, so V is 22.4 liters. So we have V, P, N, and N. All we have to do, calculate this. We have the value of the R, which is going to be 0.0821 liter atmosphere per mole per Kelvin. So there are 4 units associated with gas constants R. This is R. Liter atmosphere per mole per Kelvin. So now, this is in the book. I give you on the exam table. You don't need to memorize it. You just realize, pay attention to the unit. If you're using this gas constant, your volume must always be in liter. The pressure should always be in atmosphere. And the temperature must be in Kelvin, and you don't use grams of the gas, you use moles of the gas. Just pay attention to these units, then it's easy to solve any gaseous, any ideal gas problems. So let's look at this example. We say a cylinder of a gas contains 5 liters of oxygen. At 20 degrees of Celsius and 0.85 atm. How many grams of oxygen are in the cylinder? Do you remember that we already know from chapter 6 that if I give you grams of oxygen, you can easily convert that to moles of oxygen, or you can convert mass of any substance to its number of moles once you know the molar mass. So if I need to calculate grams, can I calculate number of moles? Once I have calculated number of moles, I can go to grams of oxygen, yes or no? So the solution to this problem is find number of moles of oxygen. What is given to me? Can I say I have the volume of oxygen? And I have the temperature of oxygen, 273 plus 20, 293 K. And I have pressure of oxygen, 0.85 atm. So if I have volume, temperature, and pressure, can I calculate number of moles? Well, do you remember PV is equal to nRT? What is unknown here? Number of moles. Do we have R? Yes, it's a constant. It's an exam table. It's in the book. Do I have the temperature? Yes, this is the temperature. 293 Kelvin. Do I have the volume? Yes, 5 liters. Do I have the pressure? Yes, 0.85. So in this equation, Pressure is known, volume is known, gas constant is known, and temperature is known. So I have to solve this equation for number of moles, right? How do you solve this equation by number of moles? How would I do that? Can I divide both sides by RT, which are coefficient of our unknown? If I do that, I can cancel T and T, R and R. So number of moles is equal to pressure times volume divided by gas constant times absolute temperature. And all of these are given already. I have pressure, volume, gas constant, and temperature, so I can calculate number of moles. Once I calculated number of moles, I can convert it to grams. Does this make sense? So let's look at the solution. Pressure, volume, temperature is known, number of moles is unknown, and I can go from number of moles to grams. As we saw on previous page, number of mole is pressure times volume over RT. Pressure 0.85, volume 5 liters. And R, 0.0821 atmosphere times liter divided by mole times Kelvin. So this is my constant R. So I'm going to actually cancel this Kelvin with this Kelvin, take this mole because it's on the bottom of this ratio, take this to the top. So that is where mole times Kelvin is coming. And the Kelvin was, of course, canceled with this. It's going to cancel each other. So the unit is left is moles only on top, only moles is left, moles of oxygen. Do the calculation, you get 0.18 moles of oxygen. Let me clear my board. And of course, you know how to convert moles to grams. I write number of moles. I want to cancel moles, write the unit I'm canceling on the bottom. I want to convert to grams. I write grams of oxygen on top, and then relate top to bottom. Can I say 1 mole is 32 grams? It's O2. Mass of oxygen is 16, right? So 2 times 16 grams per mole according to periodic table, which gives you 32 grams per mole. I hope this makes sense. Make sure to come and see me during my office hours or lab time.